up sedimentation. I think I'm close. And there's just fun stuff here at the end. At least okay, you already know that just because Monroe says it's fun doesn't mean that you think it's fun. But anyway, I think it's fun thinking about how these whole systems work and what can go wrong. So we'll begin with that. And then I want to transition to gather, and maybe you can help me think about this. I have this suspicion that there are some teams that are very close to being done for turning in the assignment today. And there are some teams that are like, there's so much to do yet, I don't know how I'm gonna get done. So I have this idea that if we could identify who are some of the teams that are like feeling chill, and if some of the members of the teams that are feeling chill could actually go and visit teams that are feeling stressed out and could help them figure things out. So that's my dream. You can think about how we might do this efficiently because I don't have a plan, but we can easily wander around and gather. So that's my idea for the second half today. Last time we met, I showed you this slide of the bottom of a sedimentation tank and all this sludge, and that it was anaerobic and that it stank. And I wanted to add this reflection, and that is, as engineers, it is very, very tempting when something like this happens, and when a system ends up perhaps not being maintained by the community because of these kinds of problems, that as engineers, it's very tempting to say, oh, that community didn't maintain the system that we provided for them. And I just want you to be aware that when you hear a statement like that from an engineer, all of your red flags should go up, and you should be saying, wait, that assumes that what the engineer did was just fine, and that all the problem is with the community. And maybe the community made a rational choice to not maintain a system that didn't work, because that is actually a very, very common occurrence. There are many, many cases where technologies get installed, they don't actually work, the community doesn't maintain it, but the community is blamed as if they were the one that didn't do the job right, when actually, even if whoever had been in the community, the same decision would have been made that it wasn't worth maintaining that technology. So things to ponder. So let's go on. This is another problem that happened in a water treatment plant. This is a view of the two sedimentation tanks looking in on the plate settlers at Agalteca. And the problem was that there were a lot of flocks coming up at the one end of the sedimentation tank. And I know that the image is not great, so I'm going to draw squares around what I want you to see. Look at what's right there. If you look really closely, that is two plate settlers laid on top of the plate settler modules to prevent any water from coming up through those plate settlers. That's pretty puzzling, right? So the reason that they did this is because there were flocks coming up through those plate settlers. And so as a rational solution, they blocked the flow through those plate settlers. And then I want to draw your attention to what I've written on the left there. For many plants, it is common for the water in the middle of the tank to be clear, yet have a lot of flock rise at the end of the tank. And then that indicates density flow. And the solution is to block off the last 10 to 20 feet of the tank so that the flocks can't rise. And that comes from this textbook, which is like a top textbook that's used by consulting firms in designing water treatment plants today. And I want to point out that it's wrong. Okay, what happened is they assumed that it was a density flow when actually it's not. But I also want to point out that this textbook recognizes this problem, and and they don't actually have a solution for how to design the sed tank so that this problem doesn't occur. So now I want to show you what we learned. So we ran into this problem, and this became a student design project to try to figure out what was going wrong in this tank. And they actually built a tiny little model of a sedimentation tank with the same kind of piping to go get the water in and get the water out. And they ran dye through it, and there was this big aha. And here's where the big aha comes. So this is looking at the side of an agua clara tank. And in this tank, the water enters in this pipe. This is the inlet channel. This pipe stub would normally not be there. And so the water's entering in that channel, going down through this pipe, which connects over here. And then all along this inlet manifold, there are holes in the bottom of this pipe. That's a kind of conventional design for distributing water into the bottom of these tanks. And it looks great. And it looks like it's going to do exactly what you want. And think for a second, the water that's coming out of the holes, there's holes, you can just barely see them, but there's holes in the bottom of this pipe. The water that's coming out of those holes, where does it go? So the pipe's coming in, it's in the bottom of the tank, near the bottom of the tank, there's holes right out the bottom. What direction does the water go? I think the obvious answer is down, right? And you think it goes straight down, right? Because the holes are like pointed down. And that's what I thought. But the water doesn't know that that's what it's supposed to do. And the water just does what's easiest. And so the water does this. Ooh, is that an insight? The water has velocity inside that pipe, and that velocity doesn't just go away because it comes to a hole. It maintains that velocity as it ducks out the hole, and it continues to have a horizontal component of velocity as it goes through that hole. And that means that in the bottom of this design of a sedimentation tank, which is what we had at Agalteca, there's this big flow path. Because water doesn't go where you want it to go, it tries to go in a straight line, right? It has inertia, it wants to go straight, and it goes straight until it can't. And so it goes straight until it runs into that concrete wall at the end of the tank, and then it turns up. And here's another key insight. Plate settlers provide almost no resistance to flow. There's no head loss. There's a tiny bit of head loss, but it's measured in, I think it's measured in micrometers, i.e. it's negligible. So the water just flows right up through those last few plate settlers. And so what they did at Agalteca is they put a block on top of those plate settlers, and that prevented the flow from coming up through those plate settlers. You see how this worked? So if you're going to solve this problem so that it doesn't happen again and you don't have to block some of your plate settlers, what do you do? And you have to go back to what was the origin of the problem? The origin of the problem was that the water coming out of the orifices didn't go straight down. It had a horizontal component of velocity. So that's what we have to fix. And it's not about a density current. It's about kinetic energy. So, well, that's what we would like to have happen. We'd like to go, actually, no, that's what the plate does on the top, but that's still a lousy solution. So insight that this is an inertia problem. This is an early attempt at solving this problem. So you see those straight pipes stuck on the bottom of the inlet manifold, and some early data suggesting that that switch actually improved performance of the sedimentation tank. So the orange data points are from an earlier system. Actually, this is for an even earlier system that also had problems. Maybe the point here is that the improvements that we've made did actually make an improvement in the performance of the plants. This is the new design for the manifold for the inlets at the bottom of this sedimentation tank. And I'll show you a couple pictures of how that's done. So the addition is those straight, what we call diffusers, that straight pipes that straighten the flow and create a nice jet at the bottom of the sedimentation tank. So this is where the water leaves it. Let's start at the bottom. This is where the water enters the sedimentation tank going into the inlet manifold. Here's the flock weir that controls the level of the flock filter in the bottom of the tank. Back in here is the flock hopper. That's where the flocks consolidate, and they do form like a liquidy sludge that then is wasted by opening up a valve. And on the left, you can see the whole bottom of the tank, and then I'll add the inlet manifold in here. So there's the inlet manifold added in. And let's look at how they fabricate these. So here they are fabricating one of these systems. They've got a drill press and they're drilling holes in the inlet manifold. I'm just realizing there's holes on the other side of that inlet manifold. So this must have been a posed picture. I had never noticed this before, right? The holes are on the other side. So anyway, presumably he's not drilling a hole right now. But the holes on the other side, the hole diameter is equal to the inner diameter of this mold. And this mold is used to slightly reduce the outer diameter of the diffusers that get plugged into that pipe. So I would love to have one of you talk through what you see in these photos. And I don't know who to pick on. How about, I would, and those of you who are not showing your video, I would love to see you. Oh, Isaac, would you be willing to share? Just tell us what you see in those two pictures and see if you can start telling a story of what's going on. You have to unmute.
Yeah, just trying to take it all in.
Yeah, and it's okay. You won't have it all put together initially, but you can start talking and see where we go.
What's going on with that Voltec? Is that like a battery, or are they weighing something?
Anyone who has an insight about what that might be, jump in.
Is that boiling water to like make the plastic more malleable and then it turns into smaller diameter? Easy to form?
That was great, except it's oil because you needed to get hotter than water. Back to you, Isaac.
Yeah, looks like they're kind of going back and forth and making those, maybe making those bigger ones in the back smaller, like he was saying.
Yeah, so where are they making them smaller?
Inside the boiling, like the right picture, and the boiling water, oil.
Okay, and what's this thing?
Can't really see it that well.
So that is an aluminum mold that has a part of it that's smaller diameter than the outer diameter of the pipe. And so when you shove the pipe in, it makes it smaller.
Looks like they're also, yeah, where your mouse is right now, they're using that to maybe shape the other side a little bit.
Yes, yes. And if you look real close, there's actually a transition in diameter right there.
Yeah, it looks like it's going from circular to almost like a rectangular.
Yes, yes. And here?
Yeah, there's like there's a change in diameter from like a smaller outer diameter to a bigger inside diameter.
Yeah, excellent. And thank you, Isaac. And there's a whole bunch of them laid over here, so they've got a lot of work to do. And for a big plant, there are literally thousands of these, and so it's a big job to mold all these. But it's just standard pipe that they take and they mold both ends. One end gets smaller so that it so that when you plug it into the manifold, it goes in so far and then stops. It goes into the place where it gets larger in diameter, and so that makes it easier to glue it in and have it actually stay. Any questions about that? That's a finished product. So now the water comes out straight. So these have to be long enough so that the flow gets straightened and there's no horizontal velocity component anymore. And then this bottom part, and notice that this inlet manifold is not centered over this jet. It's off to the one side, or it's a 3-inch PVC pipe cut in half. It's off to the one side. You might not be able to see that real clearly in this photo, but it is true. And then just this notion that we keep on learning. So in the early designs, we had a drain below this yet. So there were holes in the jet reverser to a drain pipe that was below that. And we very quickly realized that was completely unnecessary, and the jet reverser can be the very bottom, and there's just a drain at the end of the tank, and that's all you need.
I have a quick question.
Yeah.
The rectangular or like the oval parts of the bottom on the one more ahead. Yeah, that one. I'm assuming those are just to like even out the flow of the water as they like as the water like scoops up with the jet reverser, or like something like that.
Yeah, okay, so I didn't explain this. So why did we flatten the tubes? And it's because we need to have any flock that slides down this slope has got to be picked up again. So we can't have any gaps where there's no water coming down in a jet. So if there were a gap between jets, then sludge would accumulate between those jets. So we need to have water coming down in a continuous jet the entire length of the sedimentation tank, so that all the flocks get picked up. Did that make sense?
Yep, that's perfect.
Okay. Other questions? Let's talk about taking a flock filter sed system offline and then returning it to service. So this is what plant operators do, maybe every month or so, when they want to check on what's happening in the bottom of the tank, make sure there's no accumulation happening anywhere, and maybe a chance to, this might happen every 6 months, and a chance to like clean the plate settlers, because some stuff does end up sticking to the plate settlers over time, and so you need to clean them occasionally. Okay, so you need to take one unit offline, and so this is what you do. So the first thing you do is you see that red pipe? I added that red pipe in as a little pipe stub in the inlet, and that prevents water from going from this inlet channel into the inlet pipe into that tank. So I just blocked the inflow of water. And then I had to do one more thing. I have to block where water leaves, because if I don't, water will go from this tank over here where it's coming out here, and it will return into this tank when I try to drain this tank. So I have to block the outlet as well. So I blocked inlet, I blocked outlet, and I can remove the outlet manifold. I can, oh, I think I completely forgot something. In this one, and you open up the valve to drain the tank. Now you can drain the tank because you have the inlet and the outlet blocked. Then as a next step, you remove the outlet manifold, you can remove the plate settlers, and you can do whatever you want to do. And then let's put it back together again. Any questions? Okay, so we're going to put it back together. So I put the plate settlers in, I put the outlet manifold back in. And now the question is, how should we fill this tank? So what should we do next? So you could take a minute to to ponder this. This is where I wish I had you in little breakout rooms, but we'll just stay here.
I mean, I think I haven't actually looked through that.
Thank you, Patrick. So you've got two choices for how you might fill this tank back up. You got a problem. The plant is running. The rest of the tanks are in operation. The plant is running, and you'd like to fill this tank and get it back in service. And the easy thing to do would be to open up this red pipe here, remove that, and start dumping water into the bottom of the sed tank, right? It's a logical thing to do. Can anyone tell me what will go wrong if you do that? You got some tanks that are over there that are full. You got one tank that's empty. You got this inlet channel that's coming in from your flocculator. You're gonna open up this pipe. What happens next? Can you imagine? I know I'm asking you to do computational fluid dynamics in your heads. Completely unfair. But what do you think would happen? Anyone? How about this? Do you think water would go into that pipe slowly or fast?
Fast.
Thank you, Michael. Fast. Okay. And supposing you had some flocks in that water, what do you think would happen to them?
They'd break up almost immediately.
Thank you. That's exactly right. They would break up immediately because this is like one of these key insights. Flocks are actually super weak, like super weak, okay? They're weaker than snowflakes. It takes just about nothing to break them. It's not like if you pick up a flock, you can hold it in your hand. No, if you pick up a flock and try to put it in your hand, it's gonna turn into clay. It's not gonna retain its structure. So they're super weak. So if you drop them down that inlet pipe and into the bottom of the sedimentation tank, they will all break up. So now what happens if you do this? You fill the bottom of the sedimentation tank up with water that actually is no longer well flocculated. And that water is going to start coming up through your plate settlers. And because it's been all busted up, it's not going to be removed by the plate settlers. And so you're going to have dirty water coming out of this sedimentation tank when you start it up. So anyone see what you could do instead? And by the way, we didn't think about this in advance and solve this problem in advance. We did it the wrong way. And then we're like, oh, there's a better way to do this. Do you see what the better way is? Why don't we fill it up with clean water instead of dirty water? There's clean water sitting right here in this channel. This is the clean water channel that comes from all the other tanks. So we can rob some of that water and dump it back into our sedimentation tank. And so the way we do that is we open up that port, and now our effluent launder, our pipe, effluent manifold on the top of the sedimentation tank acts like a little shower, and the water actually sprays out of it and it fills up the tank. And then eventually the tank is full. And once the tank is full, we turn it on by removing the inlet pipe stub, and it begins operation, and it's full of clean water. And so it begins operating well from the beginning. Any questions?
You would have to fill it up until it like went all the way up to the entrance of the inlet manifold, wouldn't you?
That's right. You fill it the whole way up.
All right.
good. Okay. Here's some questions for you to think about. Let's do them one at a time. And as soon as you have like even a simple response of why you think this is the case, why do we use plate settlers? Who can give an answer? Why do we get excited about plate settlers? Can you give a benefit? Don't worry, even if you're wrong, I won't make you feel bad, I promise.
Is so that like, oh, sorry. Go ahead.
Is it just so that there's constantly some like ground for particles to be able to settle on?
Okay, it does provide like a surface where particles can settle on. And we could have used the bottom of the tank as that place. Why did we want to put plate settlers in?
So they don't have to go as far down?
You know, that's interesting. There's some truth to that. There's another really big advantage.
Is it so they can, with their incline, they can fall back down to recycle through the rest of the sedimentation tank to like take on more
Yeah.
particles?
So, you know, that is true. That is actually pretty important for our system. But anybody remember, like, what was it?
Reduces the velocity.
Okay, given which velocity is reduced?
Like the velocity, like the entrance, like when it enters in.
Maybe not so much, because remember I said plate settlers don't actually have any significant head loss. So if the water is coming into the tank, the plate settlers aren't going to slow it down. Anyone else? Keep on trying. There's going to be this big aha of there's one super big advantage of these plate settlers.
Is it that they just don't require any energy? They use gravity instead of.
That's true. And it would also be true of a tank that didn't have plate settlers. So we could have a tank without plate settlers, but we elected to put plate settlers in. What was the big reason?
Was it because of the costs and like they provide more surface area for settling compared to a traditional like sedimentation tank?
Yeah, so pull those ideas together. They provide lots of area at a lower cost than building a big concrete tank. So we could have built a big concrete tank, but with plate settlers, we can build a small concrete tank and put those plastic plates in, and the plastic plates cost far less than the concrete would have cost. And it's a factor of 10. And remember, you like factors of 10, especially when your boss says, I'm going to give you a raise of a factor of 10. You're like, whoo. So there's a factor of 10 excitement. We just reduced the size of a concrete tank by a factor of 10 by putting plate settlers in. And then there are other things too, like someone mentioned, you know, the flocks that come down to plate settlers go back into the bottom of the tank, and that ends up being useful. And it allows us to, in the plate settlers, capture particles that are settling slower, and down below have a higher upflow velocity where we can suspend bigger flocks. So the whole notion of a flock filter only works if you've got plate settlers above. So you can have plate settlers doing a good job of capturing small particles above, and flock filter full of big flocks and a higher upflow velocity down below. What goes wrong if you bring plate settlers too close together? So you're like, Monroe, this was a brilliant idea. We realized that we can reduce the size of our tank by bringing our plate settlers closer together. What fails when we go too far? Anyone?
Is it if you constrict the space between plate settlers, then inherently your velocity would increase, meaning your flocks would break up within the plate settlers?
So I have a tank of a certain area and I'm just dropping plates in there. And you're right that the plates themselves do have a thickness, and so they occupy a little bit of space, and so that increases the velocity a tiny bit, but that's not huge. So it's not that the velocity increases, there's something else that fails. I'm hoping there's an animation that comes to mind. There's a very sad animation. What goes wrong? I've got a certain velocity up between those plates. I make these plates really, 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 really close together. Okay, the insight is that the flock that lands on the plates, you want it to slide back down. But it can only do that if the velocity next to the plate is actually kind of low. And the velocity between the plates has a parabolic velocity distribution because it's laminar flow. And if you bring the plates really close together, that parabolic velocity distribution gets really squeezed. And so the velocity gradient at the wall is very, very high. And that means that a flock that's close to the wall is experiencing a high velocity because the flock has actual dimensions. It's not infinitely thin. And so at some point, when you bring these together, the flock goes up instead of going down after it settles. So that's the failure mode that we have to make sure that we don't do. We don't want to have plates so close together that the velocity gradient is so high that the flock that's close to the wall or on the wall is experiencing too high of a velocity that's going to carry it up. The flocks that are in the flock filter, where were they before they got to the flock filter? Where did they come from? Okay, they all came from the raw water and they all came from the flocculator, but where did they come from most recently? Somebody already talked about this. It was the animation that was weeks ago at the very beginning of this talk about sedimentation. There were green flocks and red flocks and blue flocks. There's blue flocks are in the, go ahead.
Was that the flock hopper?
So flocks do end up, blue flocks do end up ultimately going into the flock hopper. That's like the exit. That's where all the dirt leaves from the system. But where did the blue flocks that are in the flock filter, where did they come from? How did they get there?
Is it the inlet tube?
You're right, they came in the inlet tube, and when they were in the inlet tube, what size were they? Or what color were they? Remember?
They're small, weren't they?
They were small. They weren't as big as the blue ones yet. So what did they do? They were green ones, small green ones. What did the small green ones do?
They settle on the settling plates.
Exactly,
Like
they
plate
went
settlers.
right, yep, they went right up through the flock filter. They settled on the settling plates. And then what happened next? Go ahead, Victor.
Technically, they'd slowly coagulate and then fall down, and then I guess eventually they just end up in the flock hopper.
Okay, but you're right. I would use the word they form an avalanche,
Yeah.
and they aggregate as they're in that avalanche, and as they're falling down, they're blue guys, and they settle faster, and then they ideally they hang up in the flock filter for a while, and at some point they end up going over the weir into the flock hopper. Good.
I have a quick question.
Yeah.
Does the orientation of the plate settlers to the flock hopper matter?
No.
Okay.
No. You know, you think of the flock weir like a dam. It is a dam. It's just that, you know, you're used to a dam holding back water, and above it is air. Above the water is air. It's another fluid, right? A low density fluid, air, on top of a high density fluid, water. The same thing is happening in the bottom of this tank, that there's a flock suspension that is high density, and above it, there's water that is low density. It's like water and air, flock suspension, and water. And so the flock suspension flows over that dam just like water flows over a dam. Just that the density differences are so different between air and water and a flock suspension and water. This next question, how fast does the flock filter settle into a pile of sludge if you turn the sedimentation tank or this whole system off? You turn off the water going into this tank. How fast do the flocks in that flock filter settle down and form a pile of sludge on the bottom of the sed tank? What's their velocity downward if you turn the water flow off? I'm pretty sure this seems like a ridiculous question. Like, how could you possibly know this? But like so many things, it's the relative velocity that matters. So when the plant was operating, the water was going up at 1 millimeter per second, and the flocks were just hanging out there. Water's going up at 1 millimeter per second, flocks are just hanging out. Now, there's no water velocity up anymore. And so the relative velocity between the flocks and the water is still 1 millimeter per second. So now the flock is going down at 1 millimeter per second. So you can do the math. The flock filter might be 80 centimeters deep. That's 800 millimeters. So it's going to take 800 seconds for that flock filter to settle out. Yeah. And I think our timing is good. And I think this must be the last slide. Is that right? So many things. There are still lots of opportunities to learn more things. I just want to leave you with that notion. We are not done yet. Water treatment is not a completed science. There is still lots of opportunity to learn new things. And yeah, let me just, I could, for like 2 minutes. Water treatment plants have a very difficult time knowing how to set their coagulant dose. And people have been trying to automate that process for many, many decades and have largely failed. To the best of my knowledge, no one is really succeeding in pulling this off and having it work well. So we're working on this one too, trying to figure out, could we get a signal from within the water treatment plant that would give us a good indication of whether or not our coagulant dose is right or not? And the little insight that we have is that the only real place where you can get this is how clean is the water after it settles. So our trick is, grab some water out of the flocculator and run it through a little sedimentation tube as fast as we possibly can, and then run that water into a particle counter so that we can see what the particle distribution is, and then use how many particles are coming out in the particle counter of the settled water as a guide to our coagulant dose. And we're gonna try this at the Cornell water treatment plant, where they have a sedimentation tank that has a 4-hour residence time. And so there's a huge delay before they get to know whether or not they succeeded in having the right coagulant dose, right? It takes 4 hours to go through the sedimentation tank. This system will have a residence time of something like 15 minutes maybe. And so they'll get a much faster response. And so they'll be able to not be so far behind in making their coagulant dose changes. So just like there's more things to learn. And with that, I'm done. I would happily take any questions now. And I want to know, are there any teams that would be willing to split up and gather and go visit your friendly neighboring teams and give them any assistance that you can in helping to get this assignment done before spring break? Is there a team that'd be willing to split up and help others?
I would be willing. I'm not the best with feature script, but I feel like I can help out with part studios.
Excellent. So those of you who are willing to split up, I don't know how I'm kind of imagining we could do this by chaos, because you can walk around and you can see what's going on. You can, those of you who are willing to go around and visit other teams, just do that. And if you're all bunching up on one team, split up and help a different team. Okay, so I'm going to say goodbye to all of you. Have a lovely spring break, and I will see you in Gather in a couple minutes.